I thank the chairman of the Swedish Academy and of the Economics Committee, and thank you all for being here. Okay. The work on which the award was given, as you were just told, was done jointly with Amos Tversky during a long period of unusually close collaboration. He should have been here. Together, we explored the psychology of bounded rationality in the domains of judgment and decision-making under uncertainty. Bounded rationality means different things to different people. The alternative interpretation should be viewed as different geographic maps of the same territory, like a road map or a map of what is produced or of elevations. They're not really competing, they're complementary. And today, I'll be describing some of the work we did in our attempts to map departures from rational models and the mechanisms that explain them. Those are two really separate maps. One, the results, and the other, the mechanisms. This talk offers a current perspective on the early work that we did and on more recent developments. And really what I'll be talking about are ideas that were in the back of our minds when we started our work more than 30 years ago, and that were not specifically articulated, really some of them not until today, but that we very frequently discussed while we were trying to develop our more detailed theoretical and experimental work. The goals of this talk are three. First, I'd like to illustrate both the content and the style of psychological research on decision-making. Second, I'd like to review some empirical generalizations that characterize important features of bounded rationality. And third, I'd like to introduce a general hypothesis about intuitive thinking, which accounts for many systematic biases that have been observed in human beliefs and decisions. And the background idea that I was mentioning was an idea about what intuitive thinking is. And we thought about intuitive thinking as a mechanism that possibly evolved from the perceptual mechanism that humans share with other animals, and that is intermediate in many senses between this and the reasoning, the higher level reasoning mechanisms that are probably uniquely human. And we think of intuitive thinking as being constrained and in many ways reflecting the characteristics of perception. And this analogy of intuitive thinking to perception was a guiding idea for a great deal of the work that we did early on, and actually for the work that I've been doing throughout my career. And it's that analogy that I'll be trying to introduce and explain in some more detail today. So let me first introduce the general idea about perception, which has considerable implications for intuition as well. And this is that perceptual representations are selective. There are certain features that are available directly to perception, and there are other features that are not directly available. We have to compute them, or we have to perform some special mental act of transformation in order to achieve additional kinds of information. So for example, what is the area of a card? This is a question to which the answer is immediately available in perception. What is the volume of the deck? This is another item of information that the perceptual system provides us with an answer for. But what is the total area of the cards in the deck? This is not something that is given without a considerable amount of practice. Actually, no one can just see this. This is something that we could compute. It is not available in perception, and it is not available to any intuitive processing of the information. So that there are many questions, simple questions, to which you could have the answer if they deal with the area of a card or with the volume of the deck, but you would have to work in a very different way in order to operate on questions of the type of what is the total area of the cards in the deck. So the answers to the first two questions are generated in perception and accessible to intuitive judgment. The answer to the third question is not. Now, let me show you another example of representations, which this time is not a directly perceptual representation, but a representation in memory, and just watch these examples. Now, could you see the average length of the lines that you've just been presented? And for every one of you, I'm quite sure the answer is yes. We have available in the memory representation information about the average of that distribution. The answer to whether there are more red lines or black lines is quite obvious. But what do you know of the summed length of the lines, like the previous question about the area of the deck? This is not directly available. This is something that presumably you could compute by trying to estimate the number of lines that were presented and the average length and then multiplying. But intuitively, we do not have access to that particular information. So to answer these questions, we rely on a memory representation. And like perceptual representations, it includes some features, but it does not include all the features that we may need to answer different questions. So, intuitive thinking then, which I'm not going to define very precisely, but it's the kind of thinking that goes on very quickly, contrasted to the more serial, effortful processing of information that we sometimes engage in. Most of the time, we think intuitively. Some of the most highly skilled cognitive activities are intuitive in this particular sense. So chess players who recognize the chess situations instantly are thinking intuitively. In our appreciation of social situations, which is an extraordinarily refined human skill, recognizing a situation as tense or as friendly, this is something we do intuitively. However, in spite of all the marvelous things that intuition does, intuition is also prone to some systematic biases and errors. And the judgments that we make, even after due reflection, sometimes do not correct the initial impressions and the initial judgments that intuition provides us with. And even when we do correct our erroneous intuitions, we rarely correct perfectly, so that traces of the errors to which intuition is prone are found in the ultimate judgments that people do make. Now, the remainder of this talk will illustrate two central properties of perception and how they affect intuitive judgments and choice, and illustrate this idea of drawing an analogy from perception to intuitive thinking and following through that analogy to experimental consequences. The first of these themes is going to be about changes and states. And I'm just going to assert here, quite a familiar psychological generalization, that perceptual representations highlight changes and differences and basically neglect maintained states. So they are largely insensitive to the level of any state that is maintained over a period of time. Most of the information that is conveyed to the brain from the eye is about changes and differences. And to illustrate how that works, I'll give you an example from vision. The color that we see depends on the relationship between the current color and previous illumination or colors. So for example, take this screen, which all of you see as gray. Now, I'm not going to actually perform the experiment because it would take several minutes, but what we could start by doing would be to present this screen and have you stare at it for a couple of minutes. And after staring at this screen for a couple of minutes, if I return to the previous one, you would not actually see it as gray. You would see it as somewhat greenish. So that the color at which you see an object or a screen depends not really on the current stimulation, but it depends on the difference between the current stimulation and past stimulation. A familiar example from the temperature sense is the following. You can have three bowls in front of someone, a bowl of cold water, a bowl of quite warm water, and a bowl of water, tepid water at intermediate temperature in the middle. You put one hand in the cold water, one in the hot water, and you leave them there for a while. And then when you put both hands into the middle bowl, they don't feel the same experience. You feel quite warm in one and quite cold in the other because you have adapted, and the adaptation level determines our sensory and perceptual response to any particular stimulus. Now, if judgments and choice operate on representation that conform to the rule of perception, we expect changes to be salient and maintained states to be mostly ignored. And this observation, as I'll see next, has significant consequences for the interpretation of decision-making. So let's begin by an illustration, and since the amounts of money that I'll mention are large, you have to imagine that interest-free borrowing is available. And Consider the following gamble and ask yourself whether it is attractive. On the toss of a coin, you might have a 50% chance to win $15,000 and a 50% chance to lose $10,000. Suppose one multiplies by 10 in Sweden. Now, I'd like you to do something else. Well, actually, think whether you like this or not. And now, I'd like you to do something else and try to think of your total wealth and estimate your total wealth. You don't have to do it very closely, but think of a number, call it W. And now I'm going to ask you which of these two situations is more attractive to you. In one of them, you own W, and in the other, what you own is a 50% chance of having W minus 10,000 and a 50% chance of having W plus $15,000. Now, just consider the screen and the two questions on the screen, and let me tell you a little more about it. The first observation is that the first gamble is simply not attractive. And a majority of people actually, not only for such large amounts, but even when I run this on my students at Princeton, and I have them bet where they might lose $10, and I ask them how much they would need in order to accept the gamble on the toss of a coin, they generally demand at least $20. So a majority will reject a gamble with even chances to win or lose, unless the possible win is at least twice as much as the possible loss. So the first gamble is really not attractive at all. Now, the uncertain state of wealth in the second question is generally considered slightly more attractive than owning wealth with certainty, owning W with certainty. But of course, all of you recognize that accepting the gamble is really equivalent to accepting uncertainty about one's wealth. The only difference between the first question and the second question is that the first question involves winning and losing and the transient emotions that are associated with winning and losing. If you consider the problem in terms of wealth, there is absolutely no difference between the first and the second question, and there is some mystery about why preferences would be different, and they clearly are. Now, why is that important? Well, in order to see why it is important, we have to go back a long way. In 1738, Daniel Bernoulli published a famous essay which analyzed the decision problem. And the problem was the problem of a merchant who is considering sending a ship from Amsterdam to Petersburg if there is a 5% chance that the ship will be lost in winter. And before Bernoulli, obviously this is a gamble, and before Bernoulli it was considered reasonable to assess gambles by their expected value. And the expected value of a gamble is a weighted average of its outcomes, stated in ducats or kronos or dollars, where the weight of each outcome is its probability. Now, Bernoulli had a great idea, and a very important idea it was. First of all, he observed, and that's a psychological observation, that psychological value or utility does not increase proportionately with money amounts. So that, and the way he observed that was that it doesn't make the same difference to one to get an extra ducat if you own 10 or you own 100 to begin with. And he proposed that a gamble should be assessed by the expected utility of the outcomes. And utility, he meant the subjective values of these outcomes, and not by the expected numerical value of the outcome stated in dollars. So he wanted to switch, proposed a switch from dollar units to utility units in evaluating prospects. And that defined expected utility theory, which really has been changed, of course, but the basic idea is still the dominant theory of decision-making to this day, and the foundation of a great deal of work in economics. Now, I would like to argue that Bernoulli then, in addition to the great idea, made a very significant error in how he applied this idea. Bernoulli's second idea was that the merchant evaluates outcomes by considering the wealth that he will possess under different contingencies. So Bernoulli was, as he analyzes the problem, the merchant calculates if the ship makes it to Petersburg, this will be my wealth. If the ship is lost, this will be my wealth. This is my current wealth. And then a gamble is defined with the utility of these states of wealth and compared to the current state of wealth in order to determine what the decision should be. Now, in Bernoulli's analysis, if Bernoulli's analysis had applied to what you did when I showed you the previous slide with the two questions, what Bernoulli was proposing, in effect, was that you answer the first question, in which the gamble was stated in gains and losses, by transforming into the second question, in which the gamble was stated in terms of wealth. That is a direct implication of Bernoulli's analysis. And I think it's quite clear that this is an incorrect prediction. It's clearly wrong for at least two reasons, because this analysis suggests that the answers to the two questions should be the same. That is, that the gamble should be equally attractive, whether it is stated in units of gains and losses or in units of wealth. And second, let me just appeal to your intuitions here. I'm quite sure that none of you actually thought of your wealth and of adding your wealth to the outcomes in evaluating the second question, so that none of you thought of wealth until prompted. So there is something quite seriously wrong about Bernoulli's analysis. And in order to appreciate it, let's carry on a bit. Now, the assumption that final states are the carriers of utility, which Bernoulli made, was accepted without much question until recently. And Harry Markowitz, a previous laureate in economics, sketched a theory of risky choice in which the carriers of utility are changes relative to the status quo, but this was really a sketch. And the basic elaboration, much more detailed elaboration of that idea, that the carriers of utility are changes, gains and losses, and not states of wealth, that was done in prospect theory, which, as you heard, was the main work on which this year's Nobel Prize is awarded. This idea, Amos Tversky and I formulated in a paper we published in 1979, and it was later extended to riskless choice by Dick Thaler in 1980 and by Amos Tversky and myself in some subsequent work. Now, the analogy to perception and the borrowed concepts of adaptation and of a neutral reference point guided the development of prospect theory from the start, that is, from the beginning of our work on prospect theory. We were really impressed by the fact that there is something quite wrong about the idea that people make decisions by evaluating final states when perception tells us, everything we know about perception tells us that people are much more sensitive to changes and not to final states. Now, why does this matter? Well, in prospect theory, and I will not go into the theory in detail, but we have a value function, not a utility function. The value function is defined on gains and losses, not on final states. And you can see the particular shape of that function, and it has two important characteristics that entail two fairly new predictions about the behavior of people in choice under uncertainty. The first is what we call loss aversion. That is, that people are much more sensitive to losses than they are to gain, actually by a factor of about 2 to 1. And that is seen here by the fact that the function is steeper in the negative than in the positive domain. And another characteristic that, of decision-making that prospect theory, and in fact this particular graph predicts, is that people will be risk-seeking in the domain of losses, that is, when facing choices that are negative, whereas they're risk-averse in the domain of gains. Now, a question that you may ask, if an analysis that was proposed in 1738 is, at least from the psychological point of view, so obviously wrong, why was it retained in economic analysis? And I think there is an excellent reason why it was indeed retained. And to appreciate what's going on, consider two persons who got a monthly report from their broker today. A is told that her wealth went from 4 million to 3 million. And B is told that her wealth went from 1 million to 1.1 million. And now I could ask you, who are the two individuals is happier today? And the answer to that question is quite obvious. Obviously, A is quite miserable and B is quite happy. But I could ask you another question. Who has reason to be more satisfied with her financial situation altogether? And clearly here, the answer is that B, who is the wealthier, has more reason overall to be satisfied with her financial state. Now, prospect theory, where the carriers of value are gains and losses, in a sense focuses on this myopic reaction to changes. And it captures the feature, I think, that this is the way that people think about outcomes. They think about gains and losses. Bernoulli's analysis focuses on a long-term state. And that leads to a fairly important point. You can frame outcomes in two quite different ways. As we saw earlier, you can frame the same choice in terms of gains and losses or in terms of final states. Framing outcomes in terms of wealth is psychologically unrealistic. This is not what people do in general, but it is normatively appropriate. This is a more reasonable way to proceed about financial decision making, is to proceed by considering long-term outcomes than by considering the transient emotions associated with gains and losses. So that the evaluation of outcomes in terms of wealth is an aspect of economic rationality. And because economic analysis is based on the assumption of rationality of human agents, you can see the acceptance of Bernoulli's analysis as part of the acceptance of the broader idea that economic agents are fully rational. Now, let me point out without much elaboration that the standard indifference maps embody the riskless version of exactly the same error. So if you look at this map, there is one thing that to a psychologist, at least to this psychologist, I remember when I first studied indifference map, I couldn't understand them. And the reason I couldn't understand it was that something that I was looking for wasn't there. And what I was looking for was, what is the current state of endowment? That is, where is the individual now on this indifference map? Now, it turns out that in indifference map, this is not represented. And it is not represented because it is assumed not to matter. It is assumed not to matter because only endowment, which is stated basically in terms of states or a final ownership of quantities, only that is supposed to matter. Where you are is not supposed to matter. But in fact, when you do the empirical work on riskless decision-making and riskless choice, you find that indifference curves do not have quite this shape. Indifference curves show a very pronounced kink at the reference point, and loss aversion that we discussed earlier induces a very strong bias in favor of the status quo in changes between remaining where you are or changing from where you are. Indeed, loss aversion turns out to be one of the major contributors to stability in human decision-making, that once we are in a situation, moving away from it, the losses and disadvantages are more salient than the advantages. Now let me spend my remaining 12 minutes or so on another characteristic of perception that is quite important. We saw earlier in the demonstration I gave you that the basic representation of a set includes average or typical values. You certainly were aware of the shortest of the range of values, the extremely short and the extremely long lines. You had a rough idea of the relative frequency of different features, such as colors. All that is immediately available to us. But the basic perceptual representation does not include more complex statistics. For example, the sum of the length of the lines is not represented. Now, the hypothesis that I'll be presenting is the following. Many important tasks of judgment and choice actually depend on an assessment of the sum of values in a set. But because the sum of values in a set is not intuitively available, but the average is intuitively and immediately available, intuitive performance of many of these tasks is going to be systematically flawed, and it's going to be flawed in predictable, quite systematically predictable direction. And what we find in a whole family of examples, is that the judgments and choices that people make in such situations sometimes simply substitute an average for the sum, because the average is in the representation and the sum is not. And even when there is no absolute substitution, the judgments and choices that people make are generally biased, quite strongly biased, in the direction of the average. So let me give you 4 demonstrations of this in a very short time. I'll talk about evaluating a set of goods, evaluating the evidence of a set of observation, judging whether an individual belongs to a set or a category, and evaluating an episode. And I speak of an episode as a set of moments. So let me show you what these have in common. So do people average when they should add? And in all of these cases, I'll be applying a very simple test. We will take a set, a basic set, we'll call it the small set, and then we'll add values to that set. And we'll add values in the following way, so that the new values will lower the average, although, of course, if they're positive values, and they all are, they increase the sum. And the question that we ask is whether the judgments increase or decrease when these new values are added. And what already you can predict is that we're going to find quite systematically that by adding values which increase the sum, we obtain judgments that actually decrease, indicating that these judgments are at least anchored on the average. So let me give you some examples. This is from a recent study by Christopher See at the University of Chicago. Participants are shown dinnerware sets or information about dinnerware sets that are offered in a clearance sale. And there are two sets, a small set and a large set. And the small set includes 24 pieces. The large set includes the same 24 pieces and 16 others, but the added 16, there are 8 cups, and 2 of them are broken, and there are 8 saucers, and 7 of them are broken. And of course, some people don't see the labels, small and large, but they get information about those 2 sets. And they're asked to put a price on those sets. And these are, I should add that there are 2 conditions in this experiment. In one case, which we call separate evaluation, each participant prices only one set. That is, each participant sees only the large set or the small. In joint evaluation, each participant sees both sets next to each other, as you did in the previous slide. Now note that presenting the joint evaluation allows the person to apply a logical rule. That is, you know that if we've added pieces, it cannot lower the value of the set. But if you don't see that, that is, if you only see one of the sets, you are basically forced to rely on your intuitions. The rule, which we would call a dominance rule, simply cannot be applied because we do not have the data to apply it. So, these are the results. In the joint evaluation, when participants see the 2 sets together, they always pay slightly more for the large set than for the small one. This is not surprising. There's just more there, so it's worth more. But when they see them separately, they pay $33 for the small set and $23 for the large set. And this is an obvious violation of dominance, and it's contrary to a great deal of economic logic, but in fact it's a very stable result. Now what happens here is the following, I would submit. In separate evaluation, willingness to pay is anchored on a weighted average of the values of individual pieces. And that average is lower in the large set because of the inclusion of broken pieces in that set. In joint evaluation, of course, people apply the rule, and the rule overcomes the intuition. These findings are very robust, and they're not depending on hypothetical questions. They've been confirmed in a market experiment with real goods and experienced traders that I think has recently been published. Now, let me go on to the next example, this one based on work that Amos Tversky and I did many years ago. Imagine that there are 2 urns in front of you. One contains 60 red balls and 40 white balls, and the other contains 40 red and 60 white balls. Now you draw a sample from one of the urns, and your task is to assess the probability that the urn from which you drew that sample is the red urn. So what is your probability that the urn is red for these 2 samples? Here's a small sample, 3 red balls and 0 white balls, and the large sample has 7 red balls and 3 white balls. Now, the small sample actually yields considerably higher confidence than the large one. So 3-0 is more convincing than 7-3. Now, if you analyze the situation, this is wrong, and it's fairly easy to see that this is wrong. You can think of 7-3, decompose the sample of 7-3, and it's composed of 3 and 0, 3 red and 0 white, which very strongly favors red. And the other is a sample of 7, 4 red and 3 white, which weakly favors red. Now, in a logical analysis, the probability of the hypothesis is determined by the sum of the support that the 2 samples provide. But subjective confidence, in contrast, is a sort of weighted average of support. And there is strong and weak support, and the average is actually less support than the strong by itself. So here again, we see what looks like a violation of dominance in a certain sense, which is determined by this tendency to average instead of adding. This has quite serious implications. Confidence in a hypothesis is largely determined by the proportion of evidence supporting it. This is an idea that Amos Tversky developed considerably in the last theory on which he was working when he died in '96, support theory. There is also, from that same idea, you can derive a great deal of insensitivity to the reliability of evidence. People jump to conclusions when the evidence is scant, like 3-0, and they have unjustified doubts about statistics when the samples are large if the sample does not appear, or if the result does not appear overwhelmingly compelling. And one of the results, which is an important one in behavior in markets, is that there is very weak correlation between the accuracy of judgment and the confidence that people have in in these judgments. Third example. Does an individual belong to a particular category? In this example, I'll just read it to you. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice. And she also participated in anti-nuclear demonstrations. This is probably the favorite example that Amos Tversky and I made up. Now, what are the probabilities of the following events? I'll call one the low probability event. Linda is a bank teller and an active feminist. And a slightly higher probability that Linda is a bank teller, which of course includes the event that she's a bank teller and feminist. In separate evaluations, however, very consistently, the second event that the first event that she's a bank teller and a feminist is judged much more likely than the second. I had those backwards. Now, what is the theory that would explain this? The problem, again, requires judging a relation between two representations. One is the representation of the individual, Linda, and the other is a representation of the sets, bank tellers or feminist bank tellers. Now, each set, I have argued, is represented by a prototype with average features. And the similarity of the individual to the prototype is automatically computed. The judgment of similarity is then used as a proxy for the required judgment of probability. This is what Amos Tversky and I call judging by representativeness, or using the representativeness heuristic. Now, logically, the probability that Linda is a bank teller is a sum of the probability that she's a bank teller and a feminist, and a bank teller and not a feminist. But the subjective probability is governed by the degree to which Linda resembles an average bank teller, a typical bank teller. And that result leads to errors. My last example is evaluating an episode or a set of moments. And I'll actually have two sub-examples of this in 3 minutes. These data were collected from patients undergoing colonoscopy, and every 60 seconds, I won't go into details about what colonoscopy is, but it can be quite painful. They reported their pain every 60 seconds. They were prompted to report their pain. And so we have here two records of two patients. One had a short colonoscopy that lasted 8 minutes, and the other had a much longer colonoscopy that lasted 22 minutes. And you can ask yourself, who of these two patients suffered more? And it's fairly clear that B suffered more. That is, at any level of pain, B had more of that pain than A did, if you assume that they use a scale similarly, and this assumption can be defended separately. But I would like to argue that the representation of the colonoscopy or of any episode of pain is not really a sum of the pain that is experienced or an integral of the pain that is experienced over time. It is really much closer to an average of the pain that is experienced over time. And in particular, there are 2 points that play a very important part in determining people's evaluation of a global episode. One is the peak of the pain, and the other is the pain that they experience at the end. Now you can see that patient B, in that sense, is in better shape than patient A. For patient A, who had the shorter colonoscopy, the colonoscopy ended at a very bad moment, at a moment of intense pain. For patient B, who experienced more pain overall, the end was much better, and the average pain experienced by patient B was lower than the average pain experienced by patient A. And indeed, when you ask who of these two patients reported the more severe pain, it turns out that patient A was quite substantially reported substantially more severe pain. These results have been replicated in multiple experiments. It's not just the illustration of these two patients. Now, the memory of an episode, as this indicates, can be made less aversive by adding to it a period of diminishing pain. And we actually ran an experiment to demonstrate this, and this is the last experiment I'll be describing to you. In this experiment, on 2 trials separated by 7 minutes, participants immerse a hand in cold water, very cold water, until they're instructed to remove it. 7 minutes after the second trial, they're called for a third trial. They all volunteer, they're actually paid volunteers, and they know that they're going to have to experience 3 episodes of pain, and after the first 2, they're asked to which of the first 2 trials they would like to repeat exactly. And this is the structure of the experience that they have. One of these trials is short. It's 60 seconds with the hand immersed at 14 degrees Celsius. It's painfully cold. It's tolerable, but it's painfully cold. And the long experience, which they have with the other hand, is 60 seconds at 14 degrees Celsius plus 30 seconds at 15 degrees Celsius. And 7 minutes later, they're asked to choose which of these two experiences would you rather have again. And depending on the exact conditions of the experiment, between 2/3 and 80% of them choose to have the longer experience again, exposing themselves quite needlessly to 30 seconds of quite unpleasant exposure. The theory, again, is quite straightforward, and it is that if it's the average of pain that you're evaluating, then adding those extra 30 seconds lowers the average while increasing the sum. So, intuitive thinking operates on basic representations with relative little elaboration or extra computation. The basic representation of sets includes average values, but does not normally include their sum. And the characteristic results, as we saw, are violations of the logic of dominance and a general insensitivity to the size of the set. So the amount of a good, the size of a sample, the base rate of an outcome, or the duration of an episode, all of these have very little influence on people's judgments. The similarity of the results obtained in very diverse situations suggests that the same mechanism is at work in all cases. So, what I've talked about are two rules of perception that govern judgment and choice. The first one, the perceptual primacy of changes over states, which induces a myopic focus on changes in decision-making. And the second one is this idea about the representation of categories and sets by prototypes and averages, which induces a consistent pattern of errors in tasks which logically require the evaluation of a sum. And more generally, and to conclude, what I've tried to tell you is that unlike economics, psychology really does not have a unified formal theory. But a few general principles of perceptual and cognitive function both predict and explain a wide array of phenomena of bounded rationality, and I think to some extent help bridge the gap between psychology and economics. Thank you.